有没有问题 ？Any questions and comments？
Can I ask questions?
吴老师，
Yeah, Peter, thank you for a good summary. And I have some questions and have some doubts. And I just bring one first and leave time for other people to ask questions. So my first question is about the normal faulting, right? You bring up the normal faulting and you have the hypothesis. Let me reiterate your hypothesis or your theory. It is you have a mantle lithosphere delaminated, right?
Absolutely not delaminated. I won't use that word, but removed, yes.
Removed, so that you have like more like a rebound, and then you have a normal faulting and etc. So normal faulting is related to the removal, right? So the question is about the normal faulting. So what we see the normal faulting in Tibet, it has some pattern, right? I mean the extension, the normal faulting is very clear south of the Bangong Lujiang suture. It has the pattern. And but to the north, where you show this warm and slow mantle, that's the location you think there's some delamination or the removal. So why the normal faulting is more prominent to the south in the southern Tibet, not in the northern Tibet. In northern Tibet, you see some normal faults, but mostly it's the Straxler fault, and the normal faulting is it's in the minor degree. Over in the northern Tibet, you mean, for example, 97 earthquake, that's a long rupture. You see many like Straxler faulting, and normal faulting is, I think it's a secondary. So the mostly normal faulting, the extension in the south of the Bangong Lujiang suture, and it's a pattern. It's go south, cross the high Himalayan, almost also to the south. So the linking of the normal faulting extension to the removal, to me, it's like, I mean, conceptual idea is fine, man, but do you predict why this pattern match? Not just like a linking, but it's like the pattern. It's can be explained by the removal, the bond, the rebound, or.
Okay, you raise a good question. There's no question that what you're saying looks like a problem, and it may be a problem. And for the rest of you, why don't I actually blow this picture up? Indeed, virtually all of the grabens that have been dated are in the south side. This one up in here is the only one in the north. In fact, there are grabens elsewhere, but they're not as prominent. And I think, Yojing, that's undeniable. The grabens in southern Tibet are prominent. The grabens in northern Tibet are not prominent. No disagreement there. If one now how do I can't make this go backwards. If one looks at the, I'm sorry. If one looks, I have 2 points here. If one looks at the earthquakes, okay, if one sums the seismic moments, the north and the south are the same. Now, that's not that good an argument because the sum of the seismic moments depends on the big earthquakes, and one big earthquake can dominate. There's a study done by some other people a few years ago, and they ignored some of these. They made it look like this is dominated by strike slip faults. They ignored the big earthquakes. If you put what we know in about these earthquakes, and back in 2010, but also even more recently, the rate of extension you get in the north is the same. That I think is, that's hard to argue with. More importantly, is when you do the GPS, and this is Gulwei Peng's work, if you do look at the GPS, you take GPS in northern Tibet and calculate the rate of thinning of the crust. So basically you're calculating the aerial strain, but because it's conservation of mass, the aerial strain has to equal the strain or equal the negative of the vertical strain. So the thinning rate, it actually is faster in northern Tibet than southern Tibet. So we have this peculiar situation of, if we look today, northern Tibet is extending and the crust is thinning faster than it is in southern Tibet. And so then we say, well, if that's the case, why are the grabens so well defined in southern Tibet and not well defined in northern Tibet? And I don't have a good answer. A simple explanation would be to say, well, they're younger in northern Tibet. The process started more recently in northern Tibet, and so we haven't accumulated enough slip to have them as we do in northern Tibet. That might be the explanation, but I don't like it that much because I don't see, I could be wrong, but I don't see that as the explanation.
Well, I have some
Well,
doubt.
right.
Yes.
Pardon?
Sorry. Yeah. Go ahead.
So I think the point you raise is one that we worry about. We're actually, I haven't done anything on this because it's not my work, but we're trying to date one of the Grabens way up in here at the north. You may say, well, it's the end of the Kunlun fault. It doesn't really count. I don't care. The argument that it's strike slip faulting and the normal faults at the end of strikes are at the ends of strike slip faults is, to me, a non-argument. Of course they're at the end. That's where they have to be. You can't have strike slip faults end. They've got to end in something. They don't end in thrust faults. But lots of normal faults don't end at strike slip faults. So all normal faults, as far as I'm concerned, have the same value. But you're right. This is a weak point in the argument. I won't.
Well, I also have some doubt about like using GPS to get the extension in the northern Tibet is larger than in the southern Tibet. I mean, in the northern Tibet, we don't have many GPS sites. It's a hole, and that's why we put some station there, but we have waiting for data. So, but even so, like in the northern Tibet, well, yeah, so you see the hole. So when you do the extrapolation like really far, so how do you?
No, but if you want the aerial, if you want the average strain across a region, you don't care what's happening in the middle. That doesn't matter.
Oh, no.
The average is how the edges move apart. So all you want are the ones on the edges. You're right. There's plenty missing in here, but they don't matter for that question. The average.
Well, in any case, in the because like if you put like the western part, that's the meaning part of the Altentov system. That's normal for including the 2018 and 2008. It's a normal for right. I mean that's over there and to the east. But even GPS, okay, but in this part, it's well, you have 97 Lima earthquake, you have the 2001 and the Kunlun earthquake, and those are like big, super big, well, large strike slip faults and events. And even you look at the post-seismic effect, and I mean, to be honest, I didn't read the Xiaoge's the paper very carefully, but I really doubt like can really can remove that signal before you see like how much of the extension. But when we look at the topography, we see the pattern. Well, if this like extension, that's not just for GPS, it is stayed for like a geologic time scale. We don't see in the geomorphology like the GPS and
Well, your first comment about strike slip faults, yes. If you look at the sizes of earthquakes, all the big earthquakes are in the Himalaya because they're thrust faults. And normal faults never have earthquakes as big as the 2001 Kunlun earthquake. Yeah, they're big, but on this whole region. You're repeating again and again the statement that the geology, I think you mean the topography, doesn't show grabens. Yes, I agree with you. That's a weakness. But the GPS argument, I'm sorry, I just think you're wrong.
刘老师还有吗？
还有别的问题，但是我想请别人有什么问题。
好，李林。
哎，好嘞。Hey, Peter.
Hi, Lin. How are you?
Good. How are you? Yeah, thanks a lot for the talk. And you mentioned a lot about the recent criticisms of the state-by-slope paleoaltimetry studies in central Tibet along the Bangong Suture. But I may have some different opinions. So both Deng and Jia 2018 and the recent Spicer and 2020 papers, they argued that the very low state-by-slope values in central Tibet represent because of the rain shadow effect. I don't agree with this, because if you look at the modern Yalu Zambu River Valley, if we think, because this is a low elevation valley behind the Himalaya mountains, so if you think that they are experienced the rain shadow effect, so the step-by-step slope in this valley will be very negative. But the truth is that along the Yalu Zambu River from the east to west, the step-by-step slopes will decrease from the east to west, and also they are very much more positive compared with the step-by-step slopes in the high Himalaya. This is because the Yalu Zambu Valley is a very large valley, and it can transport a lot of moistures directly from the low elevations. So if we agree with this, and also we think that in central Tibet along the Bangong Suture, there is a valley during the Eocene time. So we can also assume that there will be some of the low elevation moisture transport channels that will channel the moistures from directly from low elevation to the central Tibet, but not necessarily needed to climb the very high mountains of the Gandhizi mountains. So if we believe, if you think that the rain shadow effect is correct, then the we 2016 paper argue about the low elevations using the step-by-step slopes. That will be no sense, because if there is a rain shadow, all the step-by-step slopes will be much more positive, much more negative. But with paper, the step-by-step slope is very positive. So I think that even during the Eocene time, the paleo elevations doesn't necessarily reflect the high elevation of the Gandhizi mountains, but also still the Paleosaur step-by-step slopes reflect the elevations of the valley floors.
So you make a good point. You make a couple of good points. Let me back up. I think as far as the Zangpo, the river is concerned, yes, it's a little bit lower. I don't worry too much, because the moisture doesn't go over the top of the highest peaks necessarily. It will come up through valleys. And so I don't have a problem with that. You remind me of something I hadn't thought of, but I don't have a problem. Going further north, and actually what I should do, shouldn't I? I should find a better slide to look at this. Going further north, where I think the point you make is good, and I guess what I should say is that the interpretation that I gave is definitely not unique, that there is another way of getting at this. So I want to go to this picture. So this is the Gertsa Basin, Nyima Basin, Lumpala. These are the places where the various authors have found markedly negative delta O18. Now, if this was low and open to the ocean, then of course moisture could have come into this area, and presumably did. I mean, if this is at sea level and connected to an ocean, well, there has to be a way out, for sure. Yeah. And if that's the case, then as you said, the moisture could then, instead of coming from the south to the Nyima Basin or from the south to the Lumpala Basin, could have come in on the side. Yeah. And so in the context of, I don't know how to I can back up. So in the context of this picture here, this rainfall, where I've argued the rainfall, the moisture came over this way, if we allow this other possibility, though it's the way is the author, I think, the moisture to this site actually came from the back. It came from the west. It could come in here, and this area could have been high, and therefore it could be telling us the right answer. And my mistake would be assuming that the moisture came from this direction. I think you're right. I'm right if the moisture came from this direction, but I don't know that. And as you said, it could come from another place, and hence those estimates could be right. So I will correct what I said by agreeing with you, but turning this around and saying you still cannot trust these isotope observations to get paleoaltimetry because you don't know where the moisture came. They could be reliable, but if you believe they're reliable, you are making another assumption that they didn't make, and that
I agree. Yeah.
Yeah. So thank you. I hadn't, that's a point I hadn't thought of. Good point.
Yes, I agree that I also think that during the Eocene time, there should be a valley, but the valley should have a elevation gradient from the west to east, the lower in the west, but maybe higher in the east.
Yes, yes, I agree.
Yeah.
I agree. I mean, that's consistent with what Su Tao's paleobotany has, and consistent with Wei and the work further west.
Yes. Thanks.
Okay. 陈老师，陈汉林老师，陈老师举手了。
不好意思，张老师，我不是陈老师。
哦，抱歉，我看着以为是汉林老师。哦，那你
OK
问吧。
Hi Peter, thanks. Appreciate for your wonderful talk. I'm sorry, I'm a novice about the Tibetan Plateau research, so I got a series of childish questions. So the main thing is about what you mentioned about the removal of the lithosphere fabric root. As in my mind, so which means that what happens above is the ecologization of the lower crust. Is that right? And which means we will have a thin crust. But what I have read is about the thickened crust beneath, where you mentioned the lithospheric root is removed. So it's just a.
No, that's again a good question, and I didn't go near this. Maybe I should have, but there are a couple of answers. Indeed, maybe the lower crust became eclogite, and maybe it went away. And in fact, if you look at the wave speeds of the Tibetan crust, particularly the southern part, there's a very thick zone of quite low speed material. The S wave speed doesn't even reach 3.5 kilometers per second until you get to the bottom, I don't know, 15 kilometers of the crust. So one hypothesis that's been out there, and I haven't seen it revived or resurrected in a long time, but one hypothesis is that yes, Tibetan crust actually lost through eclitization a good bit of the bottom, and only a little bit of it's left. So that in fact, southern Tibet now, with a crust that's 75 kilometers thick, if you put all that eclogite back, the crust would be close to, 90 or maybe more kilometers thick, and it's gone. That is a possibility, and maybe I should worry about it. Maybe I should learn more about it. I'm not competent with that petrology. But then you point to northern Tibet, and again, maybe it's gone. Maybe that is the reason the crust is thinner in the north, that somehow you've swept away the lower crust. I don't know, and I probably should stop by just admitting that I don't know.
All right, thank you for your help. That's all.
Okay.
Thanks to the host.
钟海。
Hi, Peter. Yeah, I'm very interested in the lithospheric removal processes. However, my question is, do you think the removal just occurred for once? I mean, it's about 10 million years ago, or there are several times? Because if just once, and the magmatic responses should be just clustered at a similar time. However, during the evolution of Tibetan Plateau, the magmatism is kind of migrating from the south to north and north to south, or something like that. So does it mean that there are several times of the lithospheric removal or not? Thanks.
Again, that's a good question. I have thought about this one, and I don't have a good answer. The possibility that you've removed it more than once is definitely reasonable to my way of thinking. In fact, the magmatic history of Tibet would suggest that you probably did remove some in southern Tibet. There's some recent papers that have argued this as well. Again, unfortunately for me, this then begins to rely on data that I'm not qualified to evaluate. So on the one hand, it's a bit like tomography. The only criteria we have for deciding what tomography you believe is you have to trust the author, but you don't ever publish that, and it fits what you already believe. So you trust what you agree with. You don't learn anything from it. Well, I feel a bit the same way with the magmatism, because I don't know how to interpret it. So the tendency is to believe what fits with what I think. And unfortunately, what I think changes with time. So I'm never sure what I believe. But I used to think that, yes, there was blobs dropped off in the bottom of southern Tibet earlier, and then this moved to northern Tibet. But I'm sorry.
Okay, fine.
You're raising a good question, and people who understand petrology should be attacking it, and some of them are, I know. But I have to find a way so that I know what to believe. I know how to decide for myself, and I'm a long way from that.
Okay, thank you. Thank you very much.
云涛，田云涛
Yeah.
，OK，
Can I ask a question about crust shortening? Could you showed us that crust shortening in the interior of the plateau occurred in ocean time, for example, in the Hawk Hill Basin and in the basins in the Bangong Suture. And also, you also showed us that these plant fossils suggest these regions were at a lower elevation. So apparently there are some conflicts, because if the shortening occurred in ocean time, that means the plateau has been built up in ocean time, because there is no significant shortening outwards. So which one you believe? Thanks.
Okay, I think you're raising a question that definitely needs to be considered. I want to go back to some pictures, because again, as I said, my own ideas have evolved on this recently in time, and in fact, maybe too rapidly. What am I looking? We're going way up here. Let's look at this. Okay, or maybe better is this. No, let's look at this. What I argued is that there's definitely shortening. Not this cartoon isn't very good. This cartoon is out of date. There's definitely shortening on the north side in here. There's definitely shortening on the south side. The Bangong Nujang Suture is right in here. No question that had shortening in Cretaceous time. No doubt about it. In fact, that's when you suture this back in early Cretaceous time. And in fact, this study, Kapp and his colleagues, they would argue that much of this shortening is pre-collision, before the India-Eurasia collision. So their view, I think, is, and now let me switch to this picture. Their view, I didn't mean to do that. Here, let me put this one up. The view would be that this area underwent shortening. Notice these dates, you're getting into Cretaceous time, and there's the Bangong Nujang Suture right here. In fact, this isn't even showing the earlier shortening. This area underwent shortening. This region down where the BNS is, this underwent shortening from Cretaceous time through early Cenozoic time, and up until about 25 million years ago, if I believe, and I don't have reason to doubt Kapp and them. Well, so there was definitely crustal thickening within the middle of Tibet, early Cretaceous into Cenozoic time. What we don't know why this region was. There's no way to know. We know the crust was thickened. I suppose there are ways to estimate how much that crust was thickened, but I don't think they're particularly good, and consequently, I don't know what to think about how this looked back at that time. Now, if I go to my cartoon, which is based to a large extent on Su Tao's work and Spicer and Deng Tao and Ding Lin and all of them, though it's different from theirs because I have to make mine different. Here it is. So if we go to this cartoon, what I would argue is, yeah, that's high. Now, was it 5 kilometers? I don't think we know. This would be low. We're talking 40 million years ago. This was high. Was it this wide? I don't know. Maybe it wasn't this wide. Was the Lumpala Basin wider than is shown here? I don't know. I think it could be. I think I drew this poorly. I think the Hushil Basin should have been higher. I drew this for a proposal. I haven't published this. If I were to publish it, I would change this picture. I would get the Hushil Basin up. So what I'm saying is that neither the heights nor the widths are very well known in this area. But this definitely underwent crustal shortening in Cretaceous and early Cenozoic time, but the basins, the shortening is on the margins of the basins, mostly on the margins of the basins, not in the middle. So the crustal shortening associated with them doesn't mean you thicken the crust here, you thicken the crust on the sides of them. That's how I answer your question.
Thanks. Can you now provide some insights about, well, speaking of crust, would you like to provide some insights about low crust?
Sorry, insights about, I didn't understand the adjectives describing crust. Insights into what kind of crust?
The recent proposals about the lower crust, like the channel flow or something.
Oh, oh, wow. Well, I don't think I can provide insights. I can give you thoughts. I'm on the fence. I don't think there's any question that you must move lower crust around. It has to move. The best paper on this, in my opinion, nobody ever cites it, is by Peter Bird back 30 years ago, 1991. And what he did was look at temperature and by association, the viscosity structure of the crust should look like, and he concluded that there was no way that it wouldn't be very soft. I mean, he could be wrong because there's lots we don't know with the numbers, but I think the Tibetan lower crust has to be weak. It has to flow. The big question is, how far does it flow? Does it simply move from underneath the Horsts and then flow and jack up the neighboring Grabens? Or does it move hundreds of kilometers, as some would argue? I find the hundreds of kilometers distance to be unlikely, but I don't have a good reason for arguing that, and I certainly wouldn't try to persuade anybody that it doesn't do that. I just don't find that to be a sensible working hypothesis. So the short answer is the lower crust must flow. How far it flows, I don't know.
Thanks.
Okay, Peter, we have 2 more questions in line. Jintang.
Okay, 好，谢谢张老师。Hi Peter, thanks for your very inspiring talk. So I have 2 questions. The first one is what caused the convective instability? And the second one is, will the instability go away when the crust is thin enough?
The instability that I'm thinking of is in the mantle, and it doesn't care about the crust. If eclogite in the lower crust is part of this, then of course the crust does matter. I should say that for me, the best example of removal of mantle lithosphere, and I don't mean delamination because as a process, I don't think that occurs, but the best example of where I think this has occurred and the evidence is strongest is actually the Andes, not Tibet. And I think one of the reasons it's best there is indeed eclogitic lower crust was part of what was removed, and it's very dense. And so the process was more spectacular and easier to see. In Tibet, I'm not sure that that's happened, but whether you had that eclogite. As I answered earlier, that's one idea that people have put out, and I just sit on the fence on that one. But the instability associated with mantle lithosphere doesn't care how thick the crust is. It cares only about essentially temperature and about the degree to which it's perturbed, because obviously if it's perturbed by too little amount, the heat will diffuse away and the instability won't grow. But crust, I don't think is important in general.
Thank you.
OK，杨丽龙老师。
Thanks, Peter. I have a question. From your observation, how long time would it generally take during the transition from surface elevating to subsiding after the removal of lithosphere mantle?
Oh, okay. That is a question I think I can answer. First of all, the removal of mantle lithosphere by this convective process is something that, I mean, it may not happen. Some of you, as Liu Jing obviously doesn't think it happens. Liu Jing, sorry, doesn't seem to think it happens, and I could be wrong about that. But the afterwards, the thinning and the subsidence, I think that we can estimate very simply by calculating strain rates. So the GPS allows this. GPS, you calculate the strain rate you want is the areal strain rate. So how fast does the area increase? And the area, because the rate that the area increases is equal to the rate at which the crust thins. So you have one number, you know the other, you multiply by -1, but it doesn't matter, you know the same number. And if you have that rate, then you can calculate how fast the crust thins. And then if you assume area isostasy, which is a decent first approximation, clearly flawed in some ways, if you make that assumption, then you can scale the rate of areal expansion, therefore rate of thinning, into rate of subsidence, and you can calculate how fast the surface would be going down. And if you put those numbers in, the surface of Tibet should be going down, but very slowly. It's something like 1/10 of a millimeter or maybe smaller per year. Hence, it's not measurable with GPS. There are studies of GPS, using GPS to get at vertical motions, and I don't believe them, but the reason I don't believe them is not a good reason. It's because it's the wrong answer, and I think that they can't measure it that well. I just don't trust it. I could be wrong about that as well. So I think you can estimate how fast things will go down. As I said, 1,000 meters in approximately 10 to 15 million years. So if you keep extending at the same rate, another 10 or 15 million years in the future, we can get together and have this talk again at that time and see whether this is right. The surface will have gone down another kilometer. I might be a little too old to be able to give the talk by that time, however.
Thanks. I found when I reading some papers about the reconstruction of the elevation by using magmatic rocks geochemistry, I found that it seems that they never consider the lithosphere rebounding. They take that as a isostatic balance. Whenever the removal of lithosphere mantle happens, they take it. They don't consider the lithosphere rebounding. So it seems that it's a question that how long will it take after the elevation by removal of lithosphere mantle?
I think that's a different question, and I think I understood your question. If you imagine you've thickened the lithosphere, and then the lithosphere comes together in blobs that sink, And of course, they draw material where then the lithosphere thins nearby. I think you're asking how fast does that occur, or what's the time scale for that?
Yeah.
And you're asking a good question if that's the question you're asking. And I think the simple answer is we don't know. We can make assumptions and we can put numbers in, and when we do, we get time scales of the order of a few million years. So in other words, you could imagine this process might start 20 million years ago, and you wouldn't really thin the lithosphere enough to see it at the surface for another 5 million years. The time it takes for the surface to rebound in response to the removal of mass is geologically instantaneous. And we know that because of Pleistocene rebound with the glaciers. You remove the ice and the surface comes up very fast. So the response, the surface response to what happens at depth is fast. The time it takes for movement within the mantle, in the convecting part of the mantle, to evolve, to change, to move, that's much slower. And we don't know. And it's worse than that because rocks don't behave Newtonian viscosity, and hence the assumptions that have to go into this are yet riskier, and it's guesswork. I think we will turn this around, and when we finally become convinced, all right, let me start that sentence again. If we finally become convinced that removal of mantle lithosphere has occurred and we have a time scale, we will use that to constrain the properties of the mantle, rather than taking what we know about the mantle and trying to calculate how the lithosphere responds to it. I hope
Okay,
I was
thank you very
clear.
much.
I said a lot, and I hope I was clear.
Yeah, thank you very much.
Thanks, Peter. I think Wang Ping is here.
Oh, 你好, Xiaochuan.
Hello. It's been a while. Can you guys hear me?
Yes.
Okay, I guess this is more of a comment and perhaps an open question to everyone. This issue of eclogite got mentioned several times. I'm definitely no petrologist, but it seems to me that, to argue that there has been some eclogite before, you have to have solid evidence. And my understanding is that the destruction of the North China Craton, the reason this eclogite hypothesis gained traction is because they actually found rocks that are best explained by the remelting of this eclogite. Is there evidence that if there were eclogite beneath Tibet, there's actually some sort of samples that we can examine at the present, or it's just a conceptual thing?
Since this question might seem to be directed at me, I will answer by saying I haven't a clue. I don't know.
Oh, it's an open question to everyone because,
right.
Like I said, I haven't read anything, but I don't read that much, so.
Yep.
刘老师。
Okay, my turn again.
Yes. Go
Sorry,
ahead.
Peter, and keep you up for so long. I have another question about Eastern Tibet or Southeastern Tibet. So you showed us Maureen Clark and colleagues' work in this region, and show that the fast incision started about 10 million years ago, and using that surface as a reference, and about up to like 4,000 meters of removal of the incision. So a lot has been going on since that publication. That's 10, 15 years ago. So we find it, and also my colleague find it's more complex than show this data. So this incision, the start of the fast incision maybe date back to 20-something million years. And even we have exhumation signal in early Cenozoic, and maybe it go back to the Cretaceous. And so this very complex, not only in the low temperature thermochron field, also in the paleoaltimetry, showing that this region has been high a long time ago in the early part of the Cenozoic. So what do you think? Have you any comment about this?
No, what you say is, I think I'm aware of all of this. And indeed, for instance, the Lungmanshan people have argued that it's not 10 million years as once was argued, but it's older. And I'm aware that many people question whether what Marin Clark has drawn here as plateau flat regions, or seemingly flat regions, may not be flat, or they may not have formed all at the same time. I'm well aware that her work, and maybe I should have not used one, her work is challenged by a number of people. I do know that. There are other studies that do agree with her, but there are many that don't. As far as the paleoaltimetry is concerned, I guess I'm less excited by that. I'm more excited by the paleobotany that's been used, which is off the map in here, not only way off the map, but there's some that's up in here. But the paleobotany, the paleoaltimetry that's been done, well, on this map down in this region, I reserve judgment on that, or let me, I guess what I'm saying is I'm more dubious of that than I am of other stuff. But I think your point is that whereas this plot that she shows here, and the one that was published shortly after by, I think it was We Met, they looked similar. There's much that looks different now. And indeed, maybe this is not representative. And maybe I should be cautious about this area. I think you have, well, I don't want to get too far into this, then personalities get involved, but I've always trusted these people, but they could be wrong. So your point is good.
王琴老师。
Hi, Peter. Thank you very much for your nice talk. I'm wondering, beyond the main body of Tibetan Plateau, the uplift history of Pamir and Tian Shan in the west is also important. One reason is because it's blocking westerly moistures. I'm wondering if you have any short comments on the first uplift history of Pamir and Tian Shan. Thank you.
Well, I have opinions about everything. I'm not sure they're valuable opinions. I'll use this as a, oh, that's not a good one. Well, all right, I'll use this as a plot. My impression, first of all, there's no, to my knowledge, no paleoaltimetry that I can't think of any paleoaltimetry from the Tian Shan that's useful. I do think that the rejuvenation of this region, or the marked initiation of rapid deformation 10 million years ago, is sound. I gave you the argument from the GPS, but all of the basins, not all the basins, but much of the sediment deposited around the southern edge of the Tian Shan and in the northern edge, including out in the Kyrgyz area, shows an increase. I should find that other slide. Shows an increase around 10 million years. That I think that's pretty good. But so there are a number of studies, most of them by Chinese. Charot is a French, very good scientist, I think. Again, all of this is in that range, around 10 or 15 million years. This is sediment being deposited in various basins. The Kyrgyz range in here, this is exhumation, the Kyrgyz range is exhumation of rock, rapid exhumation, again, presumably it suddenly rose high. The Chu, Narin, Atbashi basins, these again are all basins within the Tian Shan. This it doesn't tell you height. We don't know how high, but this timing is common. 10 million years is a pretty good number for this. Okay, the Pamir over in here, I don't think I'm not aware of very much. There's work done on the eastern side, but it's all on the flanks, and there's work beginning to be done on the western side. But as far as paleoaltimetry is concerned, I don't think we know. My guess would be that this is roughly the same age as Tibet. What we do know, we have an unusual feature over here where we have an intermediate depth earthquake zone dipping southward. So we've underthrust lithosphere beneath this region in here southward, underthrust lithosphere. My own belief is that that's continental lithosphere with thin continental crust, because I think that's the same lithosphere as you find under the Tajik Depression over here, and possibly under the western Tarim Basin. So we're actually underthrusting here. That's which you don't have anyplace else. We don't have that. Well, you do down in the Indo-Burman ranges in here, but this is an unusual situation. There's no question the crust is thick. It's something like 70 kilometers thick. It has to have been thickened. This area, much of this area was low. I think if you go back into early Miocene time, I think marine material got in, but through this gap. So this northern edge was further south. But as far as the geologic history of paleoaltimetry, I'm not aware of anything, so I don't know. I assume that this is the same as Tibet, but I'm not sure. The Tian Shan, however, I really do think is mostly young.
Okay, thank you.
Okay, one last question. 秦老师.
Okay, thank you. Thank you, Peter, for your very nice talk. I just don't want to ask question because I already wrote my question in the chatting box. I just joined the open question raised by Professor Chen about ecologites in the lower crust. According to my knowledge, so far, petrologists have not found ecologites in xenoliths. They have found granulites and amphibolites. Compared with seismic observations, and the lower crust of the Tibetan Plateau is not high enough to have higher percentage of ecologites. So I guess if they did occur in the lower crust, maybe most of them have been eliminated. So far you have the lower crust mainly composed of granulites and amphibolites. That's my comments.
Mm-hmm.
Thank you.
Thank you.
Okay. I think almost 2 hours.
Yeah.
Thank you, Peter. It is a very good talk. We see lots of fresh ideas from you and from the community. 长虹老师在吗？长老师，长虹老师。
听不懂，沙张听不懂。
I think I saw Hong is here. It's on the video.
张虹?
Yeah.
Oh, good.
常老师 is in the vehicle. See him? 打开声音吧，你声音没开，常老师。
Oh, hi,
Okay.
Peter. Oh, Peter, thank you very much. I'm going to Tian Shan, and very near. I think I heard your talk, your similar talk about the uplift of Tibetan Plateau several times, and you always add some new date. This time you put the result from Sue and Bob to your to your talk, and you think the 15 to 10 million years is very important boundary for uplift of Tibetan Plateau. And I also know some tectonic evidence after that times. I want to see perhaps after 10 million years, there are some deformations around the margin of Tibetan Plateau.
Yeah, I'm eager to find that too. But you remind me of something that I probably should have said and didn't, and that is that Tibet's a huge place, and 10 to 15 million years is a wide range. But I think that that different parts of Tibet should go up at different times. It's not like the whole of the plateau suddenly rises as if you took a box of cheese or cheese out of a box and let it flow. Different parts will go up at different times, and the different times will then manifest themselves by deformation at different times in different areas also. I do believe that if Tibet's lower mantle lithosphere has been removed, that ultimately most of it is removed, and hence there is a window of time that's important, but there's no single instant, and different places will rise at different times.
Thank you. And you know, most of my colleagues study about effects of the uplift of the Tibetan Plateau, and 3 points.
I lost him.
Asian monsoon changes, and perhaps it links to the uplift of the northeast Tibetan Plateau's growth.
Well, maybe. Maybe. Indeed, I once thought that the rise of Tibet had a big impact on the monsoon, and I think I was wrong about that. And so I'm cautious about being wrong again. So I'm steering away from that one.
Okay.
Thank you.
谢谢常老师。
Thank you.
Thanks, Peter. Should I say something in Chinese and then say goodbye to you, Peter? Sorry.
You can say all the Chinese you want. If you go on for 5 minutes, I might log off. But if you do it in 2 minutes, I can sit
No,
here.
2 minutes. Just a reminder. 抱歉各位老师，那个因为时间关系，看2个小时，老先生可能也确实有点累了。再一个，大家的问题在留言窗里边的问题，我们回头秀斌老师还有吴磊老师，我们整理了之后，我给 Peter 发了邮件，完了在邮件回复大家，这是一个。另外一个就是从今年开始，我们这个论坛的时间表不像去年那样的是固定的了，所以我们有可能2周一次，或者有可能3周一次。我们张健老师还有敖松坚老师还有我们在积极给大家争取或者后边的报告。如果像我刚才会前说的似的，如果大家有希望听到的报告，或者是有推荐的报告，或者自己能够联系到的报告人，也可以跟我们取得联系，我们把这个报告往后安排一下。另外一个呢，需要说的就是张健老师也在群里边通知大家了，本来计划今年4月底就在珠海开的这个线下论坛，由于疫情的原因，我们推迟到11月份。希望大家也在后续支持，或者是继续关注我们这个公众号。如果大家没有关注公众号的话，我一会儿在老先生退了之后，我可以再把这个公众号的这个2维码给大家展示出来。
现在可以共享的，那个 Peter 他已经退出屏幕共享了。
我担心站时间长了之后他那个啥。 就是这个二维码，如果大家希望关注的话，我们可以在这个公众号里边了解一下我们这些动态信息，有一些我们近期的一些推送也好，或者是通知也好，大家都可以在这里边关注到。还有就是我们这个视频，我已经会前的时候跟 Peter 说了，他可以共享。等回头这个秀斌老师还有吴磊老师他们准备好之后，我们在公众号里边把这个链接发给大家，完了大家可以继续从里边下载，或者是继续在线下收听。Okay, I think we are done. Peter.
Okay.
Peter,
Yeah, I'm here.
Okay. We still have maybe 10 questions in the chatting box. We will summarize all of the questions and then I will send an email to you.
Okay.
And then you can respond to my email and then answer some of the questions.
Okay. Not
Okay.
today. Tomorrow.
Yeah, not today. Not today. Not today.
Yeah, that's not in hurry.
No. Well, the truth is I'm usually in bed now.
Yeah.
Reading.
It's too late.
Yeah. Sorry.
I don't do email this late usually.
Yeah.
Thanks again, Peter, and then say hi to Sarah, and then good night.